I don't know where you lost me. I had reached slide 7. Okay. Hello?
Oh, now we can see. We can see your slide. Yes.
So I will start from the beginning once again. So I was just introducing artificial intelligence, the terminology from a very high level. It's like making the computer see, understand, and do things which human beings are capable of doing. But it's a very, very high level statement. It has many layers to it. Artificial intelligence based solutions are applied everywhere now, irrespective of domains, whether it is medical, aerospace, automotive, energy. Everywhere we are seeing application of AI based solutions. We have been using cameras and unmanned aerial vehicles for a long time now, and these cameras capture a lot of images, videos, etc. And it is possible to make use of these videos and images to extract information that is beneficial for human society as a whole. To cite some examples, if you see this picture, this is image captured from underwater cameras, but you can see that if this information is made use of to detect a person who is drowning, then it is possible to provide help to him. And through providing an alarm or alert, it is possible to bring help to him and rush him to the hospital. Similarly, this type of solutions can be used to help the blind to cross the road, etc. Then to whenever a person, old people have like fallen down because of diseases like stroke, etc., we can get help from the doctors or from the hospitals immediately. And also it can be used for predicting climatic conditions, floods, and also forest fires by making use of these images captured from these various sources. Now, it is possible to build such solutions because of 3 important factors: because of the availability of data, because there is powerful hardware like GPUs and other processing units which can do parallel operations at a very small time, a very less time. And we also have a very powerful algorithms which can extract the patterns from a very small amount of data as well as huge amounts of data. If you look at this picture, you can see that there is, whenever you start looking at this picture, immediately as a person, a lot of thoughts come to our mind, right? You can see that there is a girl child is there. She is actually enjoying the fragrance of the flowers. We even think that the lady who is standing beside the child is her mother because of the expression from her face. But to the computer or to the machine, this is just a collection of lifeless numbers. Here, since it's a 2D image in color, it represents the red, green, and blue channel information. And in order to predict something from this image for the machine, we actually have to identify the regions of interest by making use of some algorithms or programs, and then try to extract the information. For example, if the system or the machine wants to predict the emotion that is on the face of the child, first the area where the face of the child is coming needs to be identified, and after that the emotion needs to be recognized. So the algorithms are designed in such a way that it is able to locate the position of interest as well as to extract the emotion from that face. Similar is the case with other objects that are present in the image. So in order to bring intelligence to the machines, I am talking from a very high level here, we need to give an input and the system would be able to provide you with some output. Now, what needs to be done in order to give us the output that is expected depends upon the problem. For example, if you're giving the picture, here I am giving the picture of a dog, just representation. And one example would be to tell that it is a dog. Another example would be to give the picture which is shown here, and the expectation of the output would be like the baby is on the bed and is smiling. The third example would be an audio clip, and the purpose would be to understand what the audio clip is and also translate it into text. That is an example of an intelligent solution. Then coming to the medical area, if you give a CT image, then there can be a system which is intelligent enough to identify a location of the abnormality from that image. In the case of automotive, you can use intelligent systems for driver distraction monitoring or driver drowsiness detection, etc. Here, the driver is driving, but at the same time, he is texting. So the system can give a warning and also show a message. Another example would be to have a video and trying to understand what is actually happening in the video. For example, the output can be horse riding. And third, last but not the least, from a sentence, trying to understand what is the sentiment. So here, fascinating is the word that is of importance as far as the model or the solution is concerned. And it is learning from the entire context and saying that it's a positive sentiment or a positive comment. So these are some examples of intelligence being built into solutions. And I will also give a very simple example for understanding. For example, to predict a dog as a dog, the first step would be to identify the features from the image. Examples of features are the entire body, shape of the body of the dog, then the eyes, the pointed nose, ears, all these are actually features. And these features, in traditional image processing type of algorithms, we have to handcraft these features. Even in traditional machine learning algorithms, it is like that. And then once we handcraft those features and devise an algorithm to learn from the features, it is able to predict when the picture of a dog is shown to that system. But dogs are of many types. The images can come in different ways. For example, this is also a dog, but if you learn from a feature representation like this, the algorithm will never be able to tell that it is a dog. Another example is another view of the dog. That is, the entire body is not present, just the head, upper portion of the body, face, and the ears. In this case, this is another way in which a dog, all these are dogs, but there are lots of variations in the background, variations in the shapes. So devising or writing features for all these individual cases is a very tedious task. So the researchers developed, people are now making use of a technique which is based on how the human child learns. And because since we teach children by showing lots of examples, the same methodology or the same thought process is incorporated into algorithms which are called convolutional neural networks. And by showing lots and lots of images, the algorithm can be trained on such variations of images, and you will be able to recognize any object, whether it is present in any different background from different viewing angles, or whether it is dark or light or any lighting conditions, etc. The algorithm will be able to understand. So the requirement for these type of networks is that you need huge amounts of data to train the model. Of course, latest researchers have come up with algorithms belonging to this class of deep learning algorithms, which can be trained on lesser data, but of course, it needs other image augmentation techniques and creation of synthetic data, etc. I mentioned about deep learning from huge amounts of data with convolutional neural networks. And it can be trained on very powerful computers, which make use of GPUs and can be deployed on either cloud or on machines which have GPUs or on edge devices which have GPUs. But nowadays, even devices or embedded SoCs from Texas Instruments, Renesas, NVIDIA, all those, they provide edge devices which are very small or having low form factor, which can host these type of models. And we are getting the error which is reported by these type of algorithms is very less. And in the latest algorithms, even it is less than the human error. Just to include some more examples, we were seeing very simple examples of detecting dog, etc. But in the real world scenario, in ADAS applications, that is ADAS, advanced driver assistance applications, you can see it is being used in lane segmentation, then object detection and pose estimation. In the industrial scenario, compliance verification. For example, detecting whether the workers have worn helmets and other uniforms, etc. In aerospace, with the help of unmanned aerial vehicles, trying to detect the presence of defects like dents, scratches, etc. when when the flight is halted for maintenance and repair. Other examples shown here are oil wells and wind turbine blades. These are areas where it's very difficult for humans to go physically and check these defects, etc. Still they do, but if you are able to have unmanned aerial vehicles with AI solutions deployed, then it is very helpful for these type of applications. Even in the rail domain, like we have autonomous driving cases, in rail also, they are going in the direction of autonomous locomotives, where segmentation of the rail tracks can be done, railway signals can be detected. You can even see detection of switches, etc. in the rail tracks. Then the third one is an example of gas turbines and detecting the presence of defects in the turbine blades, whether it is low pressure blades or high pressure blades. And these are all vision use cases, but in the non-vision area also, a lot of work is ongoing in anomaly detection, inventory optimization, then demand forecasting, recommendation systems. If you you must be familiar with that, right? When you log into Amazon and when you try to purchase something, it comes up with a lot of recommendations, right? So recommendation system, sentiment analysis for a particular product, predictive analytics, like example is trying to predict the remaining useful life of a component of an engine or similar type of examples, and also trying to find out root cause, etc. So these are all examples where currently AI solutions are being deployed in production. And I will, this is the last example which I wanted to show you. This is again non-vision, but it is a conversational AI model developed by Google. And it is trained on a huge corpus of dialogues, open-ended dialogues, so that you can ask any question, it replies back and also gives us suggestions, it takes the conversation forward, etc. There were some controversies regarding this model, but still wanted to tell you that these are built on deep learning neural networks. So far, I gave examples of different use cases where AI is used. But behind the development of all those use cases, there is a specific set of processes that has followed that we have to follow. For example, when you are building a solution which has AI or which needs to be trained on in data, the first step is data acquisition, which is shown here. After that, this data can be acquired from cameras, it can be from databases, it can be from some, for example, data stored in cloud in Microsoft Azure blob storage or something like that. So all these are sources of data. And even data that is coming from sensors installed in the equipments, that is also an example for data that needs to be collected in order to build a model. After that, once the data is collected, there is a process called feature engineering. Before that, we need to clean the data. You need to check whether data has quality and enough quantity to build AI models. That is another important activity or process that is done before building the model. Once the data is ready, we build the models, or after selecting the algorithm, it can be machine learning algorithms, deep learning algorithms, or it can be based on natural language processing. It can be hybrid methods also. So after the algorithm is finalized and training is done, we need to deploy the model. And the model deployment can be, as I said before, on the cloud, or it can be on individual data servers, or it can be on an edge device. For example, a surveillance camera with face recognition capability. There, the model is part of an embedded device, which it can be on the FPGA or it can be on an SoC, which is part of the camera. So this is the ML workflow that is followed in order to develop a solution which finally needs to be deployed in production. But once the model is deployed in production, the challenges start. So, but we have to deploy the model in production in order to get the full advantage, right? So after deploying the AI model into the software system, we might recognize that as time goes by, the model starts decay. For example, when most of you might have built models for your final year projects or for your thesis, etc. And when you're doing a thesis or when you're doing a POC or a project, it is easy to get an accuracy of 80% or 90% or even 100, close to 100%, since most of them are probabilistic models. Getting 100% is very difficult. So more than 95% you will be getting when you develop the solution. But after you deploy it in production and when real data starts coming in, suddenly you will see that your model is not giving the results as expected. Your accuracy will go down. You will be able to get only some in the range of 70 to 80, that the end user will get, like they will be having complaints. Your customers, when it is a project done for a customer, then customer will be complaining. And so that is a very challenging situation we face when we deploy models in production. Now, what is the reason for this? There are multiple reasons. One is, while you develop the model, you might not have checked the quality of the labels associated with the data you prepared for training. Sometimes you will train a lot and overfit the model on the data that you have used for training. Then it will fail miserably when you deploy it in production. Sometimes people can introduce some adversarial noise into the data and then give it to the model for prediction, and the model will give you a false prediction. So these are some examples. So there is always chance that after you deploy your model in production, your model will not perform as expected. So here comes the need for responsible AI. This is because just consider the case of Google Translate. You all might have used Google Translate, right? And it always gives you good results. And at the same, when one person is using that solution for doing a translation, all over the world, millions of users may be using it at the same time. Even then, we are not facing any difficulty and we get our results correctly. So that is the expectation from a production quality system. When you deploy AI models in production, the same is expected for your models also. Otherwise, there are a lot of people or stakeholders who are involved, like business owner, the customer support person, IT ops person, data scientists, as well as the regulatory compliance persons, who will be coming up with questions as to why the model is giving a false prediction, whether this model can be trusted or not, whether this will lead to any regulatory issues. So many questions will come. So in this case, detecting ceasefire violations was the use case, and a model was developed for that based on video and social media data. And this particular example shows that the incident is a violation and it is giving a probability of more than 93%. But still, if you're able to give a reason to why the model gives such a prediction, then it brings confidence to the users also. So that is the level of maturity that people or end users are expecting from solutions having AI models. So now let us go a little more deeper into this. So I mentioned about the bad performance or a poor performance of a model in production. This is because models rely on real-world data for predicting, and as real-world data changes, so should the model. Because in the real-world data, sometimes suddenly, for example, in a pedestrian detection solution, while the driver is in the autonomous mode, and when the climate has changed and when there is poor lighting because of certain weather conditions, if the model is not able to detect the object or a pedestrian that is coming in front or who is going to cross the street, it is going to create a lot of problem, right? It is very risky. It can lead to accidents, etc. So even after the model is deployed in production, we need to keep track of the new data changes that are coming and make sure that the model learns accordingly. That is, there should be continuous learning for the AI models after it has been deployed in production. So this figure shows a new model which gave 100%, close to 100% accuracy, giving all the predictions right at the time of deployment. But after 1 week, you can see that its performance has deteriorated. And after 1 month, you can see that it is the model decay has started. So this should be monitored. That is very important when you deploy models in production. And when you find that your model's performance is deteriorating, again, you have another question to answer. How often should I start the continuous training of the model? Should I do it every day? Should I do it every hour? Or monthly retraining is required? So that decisions have to be made. So the current statistics shows that 87% of organizations which are undergoing digital transformation, they are struggling with low model deployment timelines. And for around 64% of the organizations, it takes a month or longer to deploy even a single model. So that is the challenge that is being faced in the production environment. So one of the solutions is to automate this entire ML or the machine learning development and deployment lifecycle. That is one of the suggested recommendation for this challenges. And that is where a lot of research as well as third-party tools as well as cloud vendor provided tools are now being developed and implemented. So this question, this point I discussed just now also, how often should I retrain the model? Monitoring the model performance in action. You can see that as time goes, you can see that the quality of the model is degrading. So where to start the retraining of the model? You will be having more and more label data coming in after you deploy your model in production, but when should the retraining start? So this has to be continuously monitored. And in the real world system, the ML code which we develop occupies only a very small portion. And ML model is not equal to the ML system. ML system has so many extra components. Like it has a serving infrastructure, that is the hardware infrastructure where the model is deployed, and the corresponding supporting libraries and software SDKs. Then there will be tools for data collection. There will be tools for data verification and monitoring. Then data analytics tools will be there. Then there will be programs and libraries for feature extraction. So many frameworks will be there. So ML code, which we develop, is just a very small portion of this entire ecosystem. We also have to consider all the other modules that are involved in a production level system. Finally, the model which you develop is getting integrated into this entire whole ecosystem of other tools and processes. So developing models is just a very small part of the whole process. So the end goal of a production deployment system should be like this. It will have an ML development module. You can see data preparation, model development, testing, and validation being done. Once this is complete, it will be deployed, the ML model as a service, into a cloud platform, or it can be on an on-premise data center. The entire process after deployment should be monitored by logging. Only then you can find out where the data drift or the concept drift is happening, and you can start the retraining of the model. And then there will be a human in the loop concept also, or that module is also there, because once new retrained models are available, whether to deploy the newly available model or not, that decision has to be made by someone who has authority. So that AI community part is there. Someone should be accountable for that. You cannot just replace an existing model with a new one as soon as you have built a new model on the newly available data. So this is the final end goal when you think of ML in production. There should be reproducibility, there should be transparency, as well as accountability. But again, the next challenge is AI software development is totally different from normal traditional software development. In normal software, you have just the code which you write in Python or in CPP or in any such languages in Java. Whereas in AI, apart from code, for example, you write codes using languages like Python, or you use frameworks like TensorFlow or PyTorch, or you even use languages like Julia, Scala, etc. to develop the models. But apart from the code, you have two more artifacts. That is, you have the data, that is the training data, and you also have the models. So there are three factors to be considered, not only just code, but code, data, and the model. That is a challenge when you try to automate or when you try to achieve a final goal like this. This shows the plethora of tools and languages we use for developing AI models. Data sources can come from Microsoft Azure Storage, from Hadoop, from Google Cloud, from SQL Server. These are all data sources from where data can come. Your data scientists can make models by making use of PyTorch or Keras or TensorFlow or even Python, scikit-learn libraries, etc. Then after that, you may be using tools like Spark or Jupyter Notebooks or ML for experimentation. These are again some of the tools that are available in market, which people use for doing or trying out with different models for doing hyperparameter tuning, etc. Then when you create your code, you need to version your code. So in software development, you may be familiar with versioning the code, your first commit, etc. Whereas in the case of AI model development, you need to version your data because the model was built using a first set of training data. After deploying in production, new data will come. So that will be a second set. So that needs to be versioned. After 1 month, again, new data will come. That will be a third set of data. So that needs to be versioned, and the models that are trained on each of these data sets also needs to be versioned. So that is another challenge we have. So all this is actually creating a lot of problems when there is no streamlined operations in practice. So that is why all the industry players have come up with solutions for this. The pain points are how to deploy a model for production after I have trained the model. So if there is some low-code deployment platform available, then that would be very useful, irrespective of the frameworks, whether you use PyTorch or whether you use TensorFlow or some other tool or Python-based libraries. This particular this deployment pipeline should be able to handle that deployment. Then how will you integrate your model into your software? That is another case. Third point is when and how often should I retrain the models? And the fourth one is how will I find out which data set was my model trained? So this is all addressing traceability, then how to retrain the models, what is the frequency of retraining. So if there is some automated platform or some set of practices for doing all this in a streamlined manner, then it will make the work of data scientists, machine learning engineers, as well as business owners, IT people, everybody's job will be very they can work in a very efficient manner. So the real world ML process will consist of hardware platforms, job management, scheduling and queuing, data and experiment tracking and versioning, and this entire set of processes. Pre-training, that is data preparation, training of the model, followed by post-training or deployment. So all this needs to be there in a system or a process flow like that. And there should be people accountable for correctly managing all these different modules. And there are some roles also in this environment. First role is data scientist role, who will be making use of the machine learning packages to build the models. Second important role is that of data engineer, who makes use of the data sources to prepare the data, clean the data, etc. Third is the machine learning engineer, who will actually deploy the model prepared by the data scientist into the production environment. And after that, there are, of course, the other stakeholders or roles like IT ops managers, data analysts, business engineer, etc. So these are some of the important roles that come into play when you think of deploying models in production. And there are multiple pipelines involved. So I will just explain the flow here. the data will be available in a data lake. From there, you take the data and prepare it. That is, remove the unwanted data, do some like transformations, clean the data, add like data imputation you can do. After that, you make the data available in a data catalog from where model training can start. The entire training process followed by evaluation. And once the best model is created, it can be registered in a model registry. And then that will be taken by another person who will deploy this into the production environment. So these are the three pipelines: preparing the data, training the model, and releasing the model. And usually these are done by three separate roles. Data scientists will do the model building. Data engineers are always involved with the data preparation, data ingestion, that type of activity. This role is very important, especially in the big data scenario. And the third one is machine learning engineer, who will take the models prepared by data scientists and then package it, validate it, and finally deploy the model in production. As a data scientist will be involved only in building the models. He will be using languages like Python or some frameworks for deep learning, etc. But integrating it into an existing system, etc., after packaging it, will be usually done by machine learning engineers and other software engineers. So usually the first two pipelines are taken care by data engineers and data scientists, whereas the third pipeline is done by machine learning engineers. So I hope you understand how these different roles play in collaboration when in the production environment. So this way of bringing together different roles and making them follow a certain set of practices, so that the entire production deployment of ML models take place in a very streamlined fashion, that is known as MLOps. So MLOps means it is bringing together, it's actually a cultural shift, and it is bringing together people, process, and platforms together, so that we get the we are able to do the deployment of AI models in a very efficient manner. So this shows actually the progression. There is a level 0, which we usually do. We, in the sense, data scientists who are involved in model development, everything we will do manually. Our models will be in our own laptops. We will write our own code. It is not shared. If some other data scientist is attempting the same problem, he will also again start building from scratch. There is no sharing of applications. So that is the drawback of a manual mode of MLOps. Whereas in ML1, in the level 1 and level 2, there is automation and there is sharing of code, there is sharing of data, there is versioning. So it becomes more and more efficient. So this shows the workflow when you have an MLOps system in place: data set, then model building, model training, model evaluation, model selection. Best model is selected, model serving on the hardware or the deployment platform, and then monitoring of the model. And if there is any drift, model drift or data drift, it is again given for retraining. And this entire process is automated. That is the most important point. Automation, the level of automation which we can achieve here actually shows the amount of efficiency we have achieved in deploying the AI models in production. There is also an important feature associated with MLOps practices, which is called AutoML. Those who are familiar with developing ML models know that there is an important activity called hyperparameter tuning. And with different hyperparameters, it is possible to develop different models also. So AutoML automatically takes care of this type of hyperparameter tuning. It builds different models, and it also tracks how much of accuracy is being achieved by each of these models. And there is lineage also as to what were the parameters that were set, etc. So almost all MLOps platforms that are currently available provide AutoML features also. So you can now understand if you're doing this manually, how much of effort we need to put to give a value for each and every hyperparameter, and then do the training, then again change the value, then check for accuracy, whether there is improvement or not. So the AutoML takes away all this burden from the data scientists and machine learning engineers, and this can be done automatically. So the benefits are actually reproducibility, collaboration, accountability, and there is continuous learning as well as deployment, and that takes place automatically, and everything can be monitored through plots, and you can see the performance and you can take the decisions, and you can even include human in the loop factor here for approval of the models and deploying it in production. These are the different MLOps tools that are available. So if you hear the topic like MLOps, it means that it is a set of practices. It is not a tool or platform. It's actually a generic term for the practices that are followed in order to have a very good streamlined process flow for deploying models in production. And lots of tools are now provided by the various industry players. Already Microsoft Azure, Amazon, and AWS, as well as Google Cloud Platform, they provide these MLOps services. Apart from that, there are third-party tools which are open source as well as commercialized, which we can use for different modules. For example, you can use for model training, you can use fast.ai or PyTorch, scikit-learn, etc. Whereas for feature engineering, you can use a platform called Feast, where for model debugging and visualization, there are offerings from Neptune.ai. Then you have MLflow, which you can use for experiment tracking. So when you, whenever the large-scale production systems are being designed by customers, they use a selection of tools from this technology stack and create the full entire MLOps stack. I just kept one example of Microsoft Azure MLOps. There is dataset management and versioning available with a declarative ML pipelines. You can create pipelines by writing Python code and you can link them together. Then there is a data drift monitor, Azure DevOps integration. That is, if there is any change in the code, not the model or the data, but if there is change in code, that is also automated for, integrating it through pipelines, and then model management, packaging, and deployment. So all these different processes are automated if you go for Microsoft Azure MLOps. Of course, cost is there because they provide it as a managed service, but you can make your deployment as well as development faster. There is collaboration and reuse, as well as there is traceability. So the key takeaways are like machine learning models are experimental in nature, as you all know, and we need to try multiple models with various hyperparameters to arrive at the best model. More than 85% of ML models do not get into production because there is a disconnect between data scientists and the IT environment where finally the model is going to be deployed. This is because there is a gap, there is a culture there is some culture shift that needs to happen, and people have to align to these practices, which is coined by the general term, which is known as the general term MLOps. So MLOps bridges this gap and is a process of taking experimental ML models to production systems. And it integrates the best practices of data scientists, DevOps team, and machine learning engineers, and so that they can work together and bring the models to production. And as I said before, the level of automation, which we are able to achieve in data, ML models, and code pipelines, that shows the maturity of ML process. And big players like Facebook, Google, Amazon, Microsoft, they all develop AI models, right? So there, everything is automated, and that is why they are able to provide us like efficient solutions, which can like scale up to millions of users as well as scale down, still without affecting any performance, latency, or accuracy. So I will stop with this. So doing machine learning without MLOps is like trying to win a Formula One race without a pit crew. This is a slide from Volvo, but very applicable in this scenario of deploying the AI models in production. Thank you.
Thank you, madam.
Now, if anybody is having doubts, it is time for you to clear the doubts. You are free to ask the questions.
So when you get placements and when you join the company where you have got offers, and if you get a chance to work in production systems, then I hope this information would be helpful just to get the concepts. How what is MLOps, what is DevOps, what really happens when you build a software for production environment, etc.
Hello, ma'am.
Okay.
So we talked about MLOps. So can MLOps be also employed in companies where it mainly doesn't utilize ML? Like DevOps can be utilized in most companies and institutions.
Yes.
So can MLOps be
No.
utilized where ML is like not the main target of the company?
It depends. If the organization is small, or if the amount of ML work is very less, then there is no need to establish all the MLOps practices which are outlined here. You can have a automated way of deployment, etc. Sometimes even, for example, if you have only 1 or 2 projects, if the company has only 1 or 2 projects, that also they are developing only POCs, they are not going into production stage, etc., because their customer may be doing the production and beyond production deployment, etc. So in those examples, in such type of situations, it is not necessary to have the MLOps pipeline.
Okay.
The team themselves can devise a versioning method for their data sets and their machine learning algorithms, as well as for their models which they are creating. Or else there are open source tools like MLflow, etc., which can work in standalone fashion also. They can make use of a Git repository also, and then manage by themselves. But if there are lots of models in production and there are lots of teams coming to work together, big projects, in such situations, going to a level 1 or level 2 of MLOps, it would be the best solution.
So I request students especially to interact with the speaker. So that is what is expected out of this kind of lecture series. We come to know various aspects
Can I
of
ask any question? We'll try to answer. You can also mail me if you have any questions. If you afterwards, when you go home and think, if some questions come to your mind, you can mail me. That I will answer.
Madam, can you post the mail ID in the chat box?
Yeah, sure.
Thank you.
So I hope no one else is having any doubts, and we'll move on to the end of the session. I, Abhiram S., on behalf of College of Engineering Trivandrum and CETA Association, extend my sincere gratitude to chief guest Sindhu Ramachandran, who spared time from her busy schedule to grace the occasion. Thank you, ma'am. I'm immensely thankful to our principal, Dr. Suresh Babu, who spared his time to attend the function and to inaugurate it. Thank you, sir. I'm also extending my sincere gratitude to the UG Dean, PG Dean, Head of Departments, CETA members, staff advisors, and other faculty members who attended the function and made this a wonderful event. Thank you, staff members. Last but not least, I extend my gratitude to my dear friends who attended this session and made it a success. Thank you all.
Thank you. So though the attendance was very less in the beginning, it came up to around 28 or so. Okay, that is good. Okay. We'll be continuing with this kind of lectures. We have planned 3 more B2C lectures. So we hope that there will we'll get more attendance. And please spread this information among the student community too. Okay, that is my request. Okay, thank you, madam. And I'm also like, I was just remembering that you are the first rank holder in Nirmala Bhavan. So I still remember
Thank you,
you.
Asha.
Okay, so we are happy that we could get to inaugurate this B2C lecture. And as Principal Sir was saying, please do, we'll invite you to the college so that we can have a physical interaction with you. Thank you.
Thank you. Thank you, Asha. Thank you, Sunita.
Thank you, Sindhu, for sparing your valuable time with us. Thank you.
Thank you. Bye.
Bye.
So the session is over, or if we can leave the session. Thank you.
Thank you, Abhiram.
You're welcome, ma'am.